Welcome. Bayesian Cognitive Modeling. We're back. Day 21. If you're new here, I recommend going and check out one of my earlier streams, but this is where I learned how to do Bayesian inference within using software associated with probabilistic programming languages such as Stan and JAGS. I learned how to navigate those softwares while interacting in RStudio, and primarily all to learn how to conduct Bayesian inference on problems that are practical for things that could come up within the cognitive sciences. As a budding psychologist, I am interested in using these tools, Bayesian inference, in order to understand decision-making processes. And so this is my adventure into learning how to conduct these sorts of analyses so that I myself can be a fluid Bayesian, or at least what someone call a hybrid, where I could use the tools when the tools are appropriate. All right, so last time we started with the chapter on multinomial processing trees, and we found that we didn't, ultimately what we found is this sort of learning effect in the data where over the span of trials for a given subject, people got better at retrieving information from clusters. People clustered and people retrieved more information. And we saw that we could specify U being this unique retrieval sort of parameter as a nuisance parameter, because we're not really interested in that. We're interested in clustered retrievals. So we could specify this as a constant, and it didn't actually impact the posterior distributions across either C or R. Yeah, that's basically what we learned here from those examples. Something else that was new or newish. No, it's just another parameterization of an interesting model. In some ways, it reminded me of the kappa coefficient example we did early on, where it involved specifying a lot of probabilities, or, well, before it was specifying a lot of parameters and inferring information in order to specify those parameters. So if we look at the kappa coefficient example in chapter 4, here, right. So we wanted to know about these parameters, which are labeled differently. Though I guess you could do this in the same sort of way that you did the other graphical model, where everything is theta, but it's a matrix of thetas, and we still parameterize the thetas using information from the three parameters, hyperparameters that we estimate, or priors. So you can see or at least I'm seeing similarities here between the examples. The similarities just being that, we had specified 3 parameters, and you could do it where they were all specified from beta instead of, but not like this. And you could have 4 of these, right? And them all pointing to them appropriately instead of specifying like this. So this is like a shorthand version, I guess. And then we had to run something not unique about this case, I'd say, is that we had to run each of the K models independently in our scripts. We couldn't run the model, or at least in Stan, you couldn't do this sort of categorical iterations. You had to just re-specify some of the initializations and the data you wanted to look at, and then run the script, even if it was the same graphical model you were trying to run it across. And I think that's part of just the nature of Stan. But I also had to do this in Stan yesterday because I couldn't find the JAX code for the processing trees example, but it did force us to write out some Stan code for the first time in the series, so that was good. Alright, so now we're going to move to latent multinomial processing trees, right? So the use of aggregate data relies on the assumption that subjects do not differ in terms of psychological process used by the multinomial process trees model. Modeling individual subjects and allowing the parameters for each subject to vary in some structured way provides one powerful way to address this issue. I'm getting some weird notification. Okay. Anyways. Okay, so the model we're going to be discussing where we're allowed to vary these parameters across subjects is going to be called a latent trait approach, which not only allows for variation in parameters between individuals, but provides an explicit model for that variation. Cool. So now individuals are going to be able to vary across parameters across the multinomial processing tree model parameters. So remind yourself, CRU are the three parameters that are like the big thing, CRU. So now CRU are also going to get sub-i's. So each subject is going to have their own CRU, and it looks like this sort of structure is what's going to inform or create the scaffolding for us to maintain or account for individual variation within each of these parameters. So I'm probably going to do a lot of back and forth here in terms of just looking at, okay, how is this model different with respect to the aggregated model? Because, I mean, in terms of sheer complexity here just being the increasing amount of nodes represented on the graph, we doubled almost the amount of nodes. So and this certainly is a lot of models to run, right? It would be a long script. If we had to run for each K last time, we had to run its own whole Stan iteration. Now we have to run Stan iterations for each of the trials for so we're just times sixing or timesing the number of subjects, right? So we have to do that process for each subject, right? Okay, the latent trait approach we adopt assumes that there are group means. So group means are here, here, and here. The values of these parameters for the ith subject. are then modeled in terms of their displacement around these group means. Okay, so this is like a hierarchical parameterization where we're going to have some mean value here for each of these, and then the variabilities, the between subject, or the variability between on the items and within on the items, I'm guessing, are all represented here, or all the within subject variability is represented by this matrix. We're using a Wishart. So I'm not that familiar with that distribution yet, but these all end up being, from my understanding, how I've seen the probit used up to this point is just to restrict it so that it's like a probability. So each of the values of these are going to be equal to some group value, and then each of the variability terms, so the systematic variation accounted on the group and the individual level, looks like. And then this is going to be every subject's going to get each of the 4 parameters, so we're just adding i's to everything here. Right, so i's. And then lastly, each subject's is going to have a k multinomial distributed for that given subject. So every subject's going to get one of these k's. Already multinomial. So in this case, we had 3 k's, right? For each of 1, 2, and 6 trial. But in this case, we'll have a matrix of k's for each subject. Right. So the only thing I'm not that clear about then is what this sort of omnibus distribution. Yeah.
I have a present for you.
Oh, stream! Look, we've got presents. Thank you. My roommate got me a birthday gift. Think Again by Adam Grant. Thanks, Hayden.
You're welcome.
Sweet. I won't get distracted with this. Well, this is a new book that just came out recently, by Adam Grant, a fairly, I'd say, acclaimed social psychologist. He's written several books. You might know, like the what is that? Give and Take, Originalists. It's the ones that come to mind. I think that's it. Or it's not Originalists, it's Originals. But he's a pretty productive social psychologist and well known for his works in, I think he did something expanding the Big Five personality model, like a 6th trait or 6th factor or something like that. Don't recall. Oh, he's also known for the introvert, ambivert or something, ambivert stuff. He's does work in, but that's what I know of him. And he's also extremely productive. I know that he speaks a lot of that about how to best structure your time and how he does it, or he models that really nicely for academics. Anyway, so thank you, my roommate. Thanks, Hayden. All right, so now we have to figure out what these group parameters that are representing variation here. Oh, it's okay. Okay, the parameters that control the displacement come from a multivariate distribution so that the variability and correlation between displacements themselves are both modeled. I don't know where we get this I from. I guess I'll find out. Let's keep going. The motivation for taking this additional modeling step is that cognitive processes represented by model parameters may often be highly correlated. Okay. Multivariate Gaussian here with mu 0 sigma equal to this distribution. So these are what? This is accounting. I think those are the distributions that are meant to be accounting for the correlations. We'll get down to it. No, cluster storage, unique retrieval for each subject. And we get response probabilities for all four for each of the trials, multinomially distributed. Now with n being the number of word pairs for a single object. All subject. But it's the same across subjects. Looks like. So these are all probabilities, the original model, but their variability is modeled using a probit transform space. That's why we have these probit transforms. Okay. So the groups on the prior group mean probit space. Gaussian, which corresponds to the probability space. So displacement parameters. So each subject gets a displacement parameter, and they're drawn from a multivariate Gaussian distribution that is zero-centered. So this is why each of these represent deviations from the average, right? The average being represented by this mu parameter, so the average of the group. The prior for the inverse covariance, where I is a 3x3. Okay, so is that a 3x3 identity matrix that has 4 degrees of freedom? Okay. So this is standard. So the 3x3 identity matrix with 4 degrees of freedom is a standard uniform distribution on the correlation between model parameters in this case, I think. Okay, so this is so these aren't different as I thought. So each of these parameters are not different in the way that I originally described them. They are a technique to get a quicker or get to a result more quickly. So it's redundancy built in, it looks like. advantage of this latent trait approach to individual differences. So I guess the question here is, why not just, right, and this is the differentiation it wants to make in this example, is why not just create this sort of hierarchical structure for each of the parameters in the model, right? So in theory, for C, U, and R, we could do what we've done in prior cases when we wanted to account for individual differences and just expand the model such that we have like this pseudo fixed and random effect structure where we specify a mean and a sigma or whatever precision or some variance parameter, thus creating distributions for each of the subject models. So it's like a hyperparameterization that builds hierarchical structure for each of the parameters in the model. But in this case, parameters are not independent of one another, they're dependent, right? And with that, we want to also, in addition to creating this hierarchical structure, we want to account for the associations between each of the parameters in the model. The covariance contains information needed to infer. Right. So this sigma gives us not only the variances for each of the, but it models the associations between them, the covariances between them, each of them. Multivariate Gaussian here. So we get this multivariate Gaussian distribution for the displacements, where we're going to get to model the covariances between them and the variances for each of the. I think I'm following. At least a little bit. The standard deviation of the clustered storage parameter, for example, is given by bloop. Another thing to just keep in mind here is the reason why we use inverse covariance matrices instead of the covariance matrix is because of a specificity of using wind bugs. Just like when we want sigma, we have to use precision. When we want a covariance matrix, we have to parameterize it as a inverse covariance matrix. Go get the code now. No, this will be interesting because I'm not sure that we're also not getting some implementation of this in R here. Well, let's see. What does it say it's in? We might just have. The code is supposed to be in MP2. MC pack. See, I'm just missing things in here. I don't have this text file it's describing. Well, you know what that means. We'll have to do it in Stan. Here's the multinomial processing tree example. Okay. Right, so 21 subjects, responses across the 4 examples, then trial. I guess we'll give it a go. So let's walk through the stand code then, in this case. So like most stand code, or all stand code, is it going to at least have a data, parameters, and model. And then we'll get additional little blocks of code when needed. These things. Good. Okay, multinomial process tree. So we have at least, we're going to specify the data being number of subjects, number of parameters, and then k is going to be some value of k. It's going to be a array of k, right? That can range from 0 to 20, because we have 21. We start at 1, but it looks like in Stan we have 0. Okay. And then there's going to be the size is going to be a number of subject by 4. So we'll have rows for each subject, and then we'll have 4 columns for each of the 4 counts of occurrences we're interested in. And now we have to transform. So transform data. I have a book here I'm going to grab. This book has a Bayesian analysis, or the student's guide for Bayesian statistics. I've been using it over the dog book, mostly because I want to circle back with the dog book. If you know about the dog book, it's like Kerchak's doing Bayesian analysis. I wanted to do that second, and I actually thought about considering doing that book as another series here on YouTube, where I'll go through that as a bigger project and try to tackle all the exercises in that book. Obviously, it would take a lot more time, and so I wanted this test run, see if I was into even doing these sort of live stream, like think aloud projects in the first place. And Bayesian Cognitive Modeling was like the perfect size textbook to undergo one of those sorts of challenges. I mean, I think I'll finish by the end of the month, which will show, in a month's time, you could go through this material and consider all the exercises. So that will be nice if we are able to do that. We might not make it, but I ultimately would be okay with that. Okay, so transform data then, right? So I'm just gonna look in my Stan textbook here. I just want to make sure I have an idea for particularly what each of these other blocks, or what they're called. So other than the data block, parameter block, and model block. Okay, transform data. So transform data can be used to make transformations to the data you pass into Stan. So this is going to look at the data I pass in the Stan, and these are carried out at the beginning of the program. It doesn't affect the efficiency of execution. So here I'm going to make a int. So int, if I'm not mistaken, are just int can be either a discrete variable or an array. In those cases, I think I'm just making a discrete variable, int, called df, and then so then for then I'm going to I'm gonna initialize a discrete variable data frame called df, and then I'm going to also initialize a vector. A vector is going to be size 3. Vectors contain continuous variables, and we'll call it multa delta hat. So 3. So vector length n, call it multa delta hat. And then we're going to make this equal to data frame is going to be equal to the number of parameters. So we're taking a transformation of our data here, and we're just going to add 1. And then we're multa delta hat, or mu delta hat. So these are going to be, I assume, are 3 processing the A, or what are they called? The clustering, C, R, the retrieval, and then the U one, the unique. Okay, so that's the transformations we're going to make. So I forgot that we're also setting up a covariance matrix here. So the covariance matrix is K by K. So it's a number of parameters by number of parameters dimensional matrix, which is symmetric, positive, definite. So all elements are equal from -1 to 1, and we're going to call that I. Okay, so that's just specifying the covariance matrix that we're going to use in order to account for the relationships between the 3 parameters. So now we're going to move into parameters here. So these are the either hyperparameters or parameters that we're going to be iterating over in order to get posterior distributions for and stuff. So we're going to create a vector, size, number of parameters, and we're going to create another vector called delta hat. And we'll call it delta hat. Sorry, I was thinking about this relationship between delta hat here and the specification of the vector. I'm going to have to look at I don't have a good example of these specifications with a vector and then this thing and then a vector. Okay, there we go. Vector. I think what's happening here is I'm creating a vector, and then for each of the dimensions of the vector, vectors in stand are column vectors declared with a size, the size being dimensionality. For example, a 3 is declared, I'm going to call it U. You can do this with constraints. Okay. Oh, here we go. Vector expression. So this is an example of a vector expression. Square brackets may be wrapped around a sequence of a comma-separated primitive expression to produce a row vector expression. So for example, the expression, here, I'll pull this over to the screen so we can take a look together. So here, this is sort of what I was trying to capture, right? Where it looks like that's what's happening here, where we're saying a vector and then we're saying what the vector is. So applying the transpose operator, small vector in a single life. So it's setting up So this is like a matrix expression here. A matrix expression consists of square brackets wrapped around a sequence of column. So we have this vector here too, and we then have the delta hat, which is going to be each of the number of parameters are going to have number of subjects. I think that's what's happening. All right, I just want to get through to run the code here. Covariance matrix, we call it sigma, and then these are real values. So real, keep in mind. Just a continuous variable. So this is three unbounded continuous variables representing the estimations of mu for each of the three parameters. The main parameters from the multinomial processing trees model. And now we have these guys. 0 to 100. And now we're transformed. So now that we have the parameters in the covariance matrix. Now we transform those. So a simplex is a vector size 4 of non-negative continuous variables whose sum is 1. Whose theta, right, so when all the thetas add up, they equal to 1. And this is for each subject is getting one of these. So this is like adding an I. So vector number of parameters, delta hat I. It's like an I maybe. So we do 4 of these for each of the subjects, right? So we do a vector of parameters for each of the subjects. And then we have these vectors. So we're taking n subjects. Where do we specify n subjects? And subjects specified above. So C, where do we specify C? C is a vector here, here, here. So each subject gets one, and then row, matrix parameter. Oh, so these are transform parameters, yeah. And also a symmetric matrix, we'll call it row. This is our correlation matrix. And then we have vectors for the delta hats, which we specified. What makes a transform parameter different than a parameter? There are occasions when you want to generate samples for transformations of parameters. Alright, there are occasions when we want to generate samples for transformations of those parameters defined in a parameters block, and possibly even samples of these transform parameters. So this is part of the hyperparameterization. So we want to specify simplex. Okay, so this is just, I see why I'm looking above and not seeing them. These are just creating the containers, right, for the transform parameters, to which for one for each subject, delta hat at that subject is going to be equal to delta hat, which we specified here. And then I'm going to make this equal again because I know that that is deprecated. And so changing it now. And then we probitized these CRNUs. CRNUs were initialized up here. And CRUs are made up of parameters, right? So this is why this makes sense. So this is why it's in transform parameters. So this value here are set up, then we use those values plus these values or times the sum of these values, probitize it. And that's going to give us the distributions of C, R, and U, which we're interested in. And then we specified these thetas, right? Or we specified a simplex for theta, yeah. So simplex for theta here, so for within each subject then, we're going to be able to calculate each of these thetas using these parameters. So it's running, and then we do that for each subject, good. And then for I1 in the number of parameters, take I2 in the number of parameters, and then, so this is us getting at the right point in the matrix. So if we were looking at 1, 1, for example, so the first parameter being the variance parameter for, parameter 1. Where did we calculate sigma? Sigma's from the covariance matrix. So we're taking the values from the covariance matrix, and then we're transforming them so we can get correlations. So we're just estimating R using covariances and variances. Okay, now we're at the model stage. So models, this is our likelihood. We specified both the likelihood and the priors in this block. First, and then these as well. Here. And now each of the priors, so we specify priors on informative for each of the mu's, and then we specify the covariance matrix here to Wishart with the degrees of freedom 4, and I, what we specified above. So we have 3 parameters plus 1, 4, and then here we got I. So delta hat, multinomial, so multivariate normal, delta hat. So this is capturing all of the CRU with sigma here in each of their mu's. And then for the data, counts are distributed multinomial with this rate. And then generated quantities is the next. Generated quantities is probably the fourth most used block, it says here, so. And it's used to do posterior predictive checks on the fit. Okay. So we're just specifying to do some post checks here, it looks like. And I have to change all these to equal signs again. Alright. Number of parameters. Identity matrix is going to be 3. The initializations for each of them. So keep in mind we're going to use 3 chains here, it looks like, and then we have to initialize delta hat, sigma, each of the mu's, each of the variance parameters. Xi. So C psi, R psi. Okay. And then the parameters we're interested in are the averages and the averages, the variability across each of the main parameters, and the correlations. And iterations, warm up, K is equal to response 1. What? What is that? Okay, I see. I don't know what that equals. It's the data set. So here's the first data set. And then here's the... Let's see what happens. Might just catch a crash really quick. Good starter crash. And then we'll do response 2, and then response 6. So still we're running models for each of the responses, but now we're capturing individual variability across the parameters within each of the response trials. Once we get this first one done, we should be pretty quick. Because it will just run on using the history. Uh-oh. Looks like it wants a little more warm-up. Looks like we're stuck. Oh, there it goes. But it's struggling. This should work better. Oh, we're really moving slow. Okay. This might work. I gave it more gas, but that might make it take longer. But it looked like the reason why I was having issues was because I didn't give it, or at least that's what it was telling me here, that not enough iterations in the warm-up. So that might have been causing some challenges. So I just increased the sample iterations pretty big. So this actually might just take a long time. So let's look at the question. Okay. What do you conclude about the posterior distributions in figure 14.5 about learning over the course of trials? Compare your conclusions to the original model. Okay. Well, here, let's see, we have the averages for each. So here we still see this effect of increased retrieval from clusters. Big increase from clusters. Additionally, we see the same thing for the probability of clustering as well. However, one thing to note is the spread of these distributions. So there's a lot more meat, if you will, or variability within our estimates. And this is particularly clear for me when we're looking at mu sub c here, where they seem to be less precise. That makes sense because we're accounting for additional variability. Let's see. Excuse me. All right, so this is good. So it looks like we're making some progress here. Yeah. We're already moving a little bit quicker now, you see. That's interesting. But we're getting past that warm-up phase. So chain 1 is sampling, chain 2 is sampling, chain 3 is sampling. Okay. So they're all chugging along. Alright, so let's continue talking while we wait for that. Keep in mind this is only the first trial. But if my intuition is correct, the second one should be more quickly. Ooh, we're freezing. Okay. And here is the correlations. So looks like we have the correlations here between each of the here's the correlations between C and R, which looks like they're pretty centralized around 0. Although for the third case, they increase slightly. So that's good if there was the case that they were different. Then this would be sort of evidence that as we have more clustering, we'd have more retrieval of clusters. So that sort of theoretically would make sense in my mind. And this is clustered correlation with ultimately, I think that each of these rows are just demonstrating, look, we're accounting for correlations, and the correlation ranges quite substantially from -1 to 1 for each of these parameters. Though there is some sort of deviance between, for correlations that involve C, it looks like. But otherwise, we see on average larger values, right, for each of the mu's. And these conclusions are the same with respect to what we saw from the first example. Okay. Now extend your WebBug script to collect samples from the prior distribution for the standard deviation and correlation parameters. This involves including variables sigma prior, sigma prior, rho prior, sigma priors, sigma prior, sigma prior. Examine the prior and posterior distributions for the standard deviation and correlations. What can you conclude about the usefulness of the correlation parameter and the latent trait? So we do this, right, here. Or we don't do that. Though this is going to be one of those issues where, in this particular example, because of computational time and just time, and I'm going to highlight this and see if I can. So this particular case, editing code to do this. Oh. Okay, so it seems like the answer to estimate this sort of model, we are going to need to substantially increase the we'd have to increase the sample size. Not getting traces. Okay. What's up?
Your alarm went off. You know what time it was for?
7.
What you doing?
Almost done. I'm at about an hour.
So another hour?
There we go. And look at the chains here. looks like 3 parameters we just couldn't estimate. Ooh. It looks like something going on here. We had like this. Oh, I've never seen that before in a chain. It looks like it got stuck. Right, so those are issues with sampling. So this would potentially be something where the warnings that Stan gave me told me I would just increase the sample estimate. And then these, it looks like I just couldn't get estimates for, but if you look at them, they're supposed to represent variances, right? Oh, no, sorry. These make sense, right? Because row 1, 1 is just a correlation with 1 to itself. So each of these should be 1 no matter what. Though we are definitely seeing this issue here. I'm getting stuck somewhere. I'm going to ask my professor about that. And I'm going to take a picture. And ask him what that means. Make sure I get the whole deal. My guess is that it's like getting trapped somewhere. And they're being really dependent on one another. Latent trait approach deals with parameter heterogeneity as a result of individual differences between subjects and relies on data that is aggregated over items. In many applications, however, it's reasonable to assume that models do not differ between subjects but also between items. For example, it might be easier to cluster some pairs of semantically related words than others. This suggests it's a multinomial processing trees model that incorporates both subjects and item variability. Okay, so well, we wouldn't be able to do this because the data is aggregated in subjects. Right, so if you look at the response ones, here for each subject, I don't have item variability. I'd need information about each of these items, right? Because I only have information about subjects and where each of these items lied. It's sort of like the same problem we had before where I wouldn't be able to use the data from the first case in order to answer the subject questions because it was aggregated across trials. But now we're aggregated across items, pairs, within subjects. But what we would do, graphically speaking, would be to each of these would get a J. So we'd have Cij, so C for the individual subject for an item pair, right? I think. And then we would just model the averages for the item pairs in addition to the average C's for the item pairs in addition to each of these parameters. So we'd have like a big another square that had, or you could do like or it would be a second plate that would have these three would be contained within it. And then we'd still have these three over here, but now we'd have another 3 parameters, these displacements and the averages for the items And then we would have this omnibus still sigma inverse capturing all the associations between them, or we would have two of them. I'm not sure if we'd want to capture, oh no, we'd want the correlations between the items and subjects, right? Or we'd at least like to capture variability for the subjects and the items. So to do so, it's not, I'm not sure, I'd have to create a where is it, another sigma, or they all get embedded in the same sigma. Part of me wants to say you just get J's for all these things, right? And it looks the same. Or we're capturing something different where there really is just item-specific displacement and item-specific averages. So the average cluster, average retrieval for an item. But we don't average retrieval for an item for a given subject, right? So you could model variability that way. So this model can extend broadly, and that would be the cross-random approach. That would be the ultimate psychological model, right? Or the current vogue thing where we want to account for item and subject variability at the same time. So that next extension of this latent trait model would be like a latent trait multinomial processing tree model that accounts for variability of both subjects and items. So I'm just saying the same thing here, but it just and I think this README might have done it. It does not. But I could take a look. Right, so this is the parameterization the text was talking about, with just getting posterior predictive checks for each of the models in addition to sigma, in addition to the parameters. So we parameterize, get the mean standard deviation correlations, but we also get the mean standard deviations and correlations for the prior. So this is a way to assess fit. Right, so it's a diagnostic approach using predictive checks. But yeah, that looks like what we're going to cover today. And then looks like next time we'll move into the simple model of memory, a scale invariant memory perception and learning model, 2007. Maybe I'll be able to do a little prep reading beforehand, but because this looks like it's going to be layered with items within items and conditions. So that looks interesting. And even with these later examples in the case studies, we're seeing that we're meeting our computational limits, right? So I wasn't even able to execute all the models for each of these. So next time I'll try to do that, and I look forward to doing that with you. So have a good day.